In this section, we deal with a series that has its terms alternating in sign. So an alternating series is a series whose terms go positive, negative, or the other way around, negative, positive, negative, positive. Every term must change sign when you go to the next term. The alternating series can be expressed in one of two forms. It is -1 to the n b sub n, or -1 to the n plus 1 b sub n. So in other words, that -1 to the n is giving us our flip-flop sign. Now it could be -1 to the n plus 3, n plus 2, n plus 5, but it's that negative part, the alternating sign, and then b sub n, where b sub n is a positive number. So that's what constructs an alternating series. The sign part which flip-flops and the rest of it. If you expand out an alternating series, it looks like b1 minus b2 plus b3 minus b4, or the same thing with all the signs flipped. And your b sub n's are always greater than 0. Now we have two bits of information. If we know, first of all, that b sub n plus 1 is less than b sub n for all n. This basically says is that the b sub n's are decreasing. Really, there needs to be, from one spot on, all these terms are going to be decreasing. So it doesn't have to be all the b sub n's, but like b sub 5 on, everything after that will be decreasing. The next thing we need is the limit as the b sub n goes to 0. Now condition 2 is really the test for divergence. If the b sub n's don't go to 0, then we know by the test for divergence the series will diverge. Now if we have condition 1 and condition 2, then we get that that series is going to be convergent. Guys, I want y'all to realize that the alternating series test never tells us a series will diverge. So your alternating series test never says anything about divergence. It just says if you meet this criteria, it's going to converge. Hidden in the alternating series test is this test for divergence. So our test for divergence can give us that a series will diverge. The alternating series test can only tell you if something converges. Now you may ask, well, why does this work? Well, if you think back to, let's scroll up here, b sub 1, let's just assume the first term's positive and then they alternate signs. If you think about your running total, so let's make this a little larger. There we go. And so we look and say, okay, well, b sub 1. So b sub 1 is some value, it's positive, it goes up to this line right here, and I get s sub 1. So b sub 1 and s sub 1, that's our first partial sum. Now b sub 2 is negative in front of it, the sign in front of b sub 2 is negative, so that means I'm going to be basically adding a negative number, so it means I go backwards a distance. Now because it is a decreasing set of values, when I go backwards, I don't go back all the way back to where I started. I go back shorter than b sub 1. That gives me s sub 2. b sub 3 is once again positive. It's smaller than b sub 2, so when you add b sub 3, you're going backwards or going forwards again, but not as long as b sub 2. So in other words, you're flip-flopping back and forth. You always go back a distance shorter than the previous term. And so you tend to flip-flop, jump back and forth, and if you do this forever, your sum is in the middle. So pretty much you can say I can go as far as I want. I'm going to flip-flop back and forth, jump from one side of the sum to the other side of the sum, always getting closer until I finally get so close I pretty much have the sum. Now, as with all the other series, this one will not tell you what the series converges to. It just says, hey, it converges. Now, our first example here says, does this series converge? Now, if we look at this, our a sub n is minus 1 to the n times 1 over n, which says our b sub n is our 1 over n. So the alternating part is the minus 1 to the n. Our b sub n is the 1 over n. And so we look at our b sub n's and say, okay, well, is the limit as n goes to infinity of 1 over n equal to 0? That's a check. Are the b sub n's decreasing? That's a check. So if it's a constant over a polynomial, then yes, you're going to get that this thing is going to be decreasing. 1 over n squared. That's sort of obvious. You could always take a derivative to verify. So we got our two conditions. By the alternating series test, this series will converge. Now we have no, well, I should say, y'all have no way of figuring out what it converges to. Okay, it's not geometric, so you can't find a sum. It's not telescoping, so you can't find a sum. All you can tell me is that it actually converges. If you use some other mathematics, you'll see that this actually ends up being natural log of 2. This is just extra information if you're just sort of curious about it. We don't really have the way of finding that out as of right now. And so here we have a series. It converges by the alternating series test. Now, just like when we work with series using the integral test, for an alternating series, we can also talk about how accurate our estimate is. If I add the first 10 terms together, what type of error do we have? So we have an error estimation. If we know that an alternating series converges to some sum, we don't know what the sum is. Now, it tells us, this statement says that, hey, we know that it's decreasing and the terms go to 0. So if you know an alternating series converges by the alternating series test, then you have this information. You know that the absolute value of r sub n, in other words, the absolute value of the error, we don't care about if this extra bit is more or less. We just say, okay, absolute value of that. By definition, that absolute value of the error is equal to the absolute value of s minus s sub n. And we find that that is less than or equal to b sub n plus 1. It'll actually be less than, but our textbook has the less than or equal to. So basically, this translates into plain old words, is that the error is less than the next b sub n. Now let's see why that is going to be a true statement here. So here is our chart again, and we're assuming our terms start off b1 minus b2, just like in the first page of the notes. So if I look at s sub 2 right here, in other words, we have s sub 2 is b1 minus b2 for this picture. Then we're going to have an error here. This distance right here would be the error, or in other words, r sub 2. So that green distance is how far off we are by just adding the first two terms together. Now if you look at our term b sub 3, b sub 3 in magnitude goes all the way to there. Notice that my error, r sub n, should call it r sub 2 here, is less than b sub 3. If I look and say, hey, let's go all the way to s sub 5. So s sub 5 would be b1 minus b2 plus b3 minus b4 plus b5. So we get to there. Then this error here, in other words, R5, is this distance. It is how far away are we from the sum. And we see that b sub 6, while it's going backwards, its magnitude goes all the way back across the sum to the other side. And so we see here that, hey, R sub 5, that error is less than our b sub 6. The key about the alternating series is when you add the next term, you're always jumping across the sum to the other side. So that always goes from whatever partial sum you have back to the sum and then some distance. So that distance between the sum and the partial sum, that error, how far you're off, is always smaller than the next term. Now this problem says, find the bound on R sub 4. So if you look at this, we basically did this series a while ago. We know it converges by the alternating series test. Now you may say, well, this series starts off at n equals 3. The one we did before starts off at n equals 1. Well, really it doesn't make a difference. Because if you start off at 1 and you know all these terms are decreasing and the terms go to 0, by starting off at 3 you have the same conclusion. So the starting point doesn't tell you really much on convergence or divergence. It is what does the ending of this series do, or what the terms do. The starting point affects what this actual sum is, and it will affect our error estimate. So if you think about it, since I recognize that it's not starting off at 1, I mutter under my breath, my inner child is upset. And I look at this and say, well, let's just write this out. So when I plug in a 3, that's minus 1 cubed, so that's going to be a minus 1 over 3, plus this is 1/4, minus 1/5, plus 1/6, minus 1/7, plus 1/8, and it just keeps going on. Now, once you see a series expanded, then we're back to our basic definitions. S sub 4 is the sum of the first 4 terms. R sub 4 is everything else. That's basic. It is, S sub 4 says, add the first 4 terms together. R being remainder, the error, how far you're off, is everything you didn't add. And so our alternating series test says that R sub 4 in absolute value, because we don't want to care about if it's bigger than the sum or less than the sum. In other words, what type of error are we dealing with, positive or negative? Well, that's less than the next term. Now, the next term, folks, is the 1/7. Disregard the negative sign. Our next term is just 1/7. So we're looking at the b sub n's when we talk about our error. Don't care about the sign. Whether that term's positive or negative, you always use the positive value. And so we see that the error is less than 1/7 if I use only the first 4 terms for this series to approximate it. Now we look at some series and try to determine if they converge or diverge. So our first problem, part A, summation n equals 1 to infinity minus 1 to the n, natural log of that quantity. When we look at a series, we first think about, okay, what do we know? The big key here is this minus 1 to the n. That tells me that this is an alternating series. So if it was geometric, I could still use the geometric information. But once I recognize it's an alternating series, then my first thought is, well, what's b sub n? In other words, what is the term without the flip-flop sign? That is my natural log of 1 plus 1 over n squared. So I've determined it's an alternating series. I then find b sub n. Now, Remember our alternating series information, we need 2 bits of information here. I need to know, well, first of all the b sub n is greater than 0. If I flip-flop back, come back to this page, there it is. Well, natural log of something, as long as this is bigger than 1, it is greater than 0, so yes. I also need to know, are the terms decreasing and do the terms go to 0? So let's try the terms going to 0 first. The limit as n goes to infinity of this natural log of 1 plus 1 over n squared. And we see that's natural log of 1 equal to 0, so the terms do go to 0. That part's taken care of. And now we look and say, well, is it decreasing? Well, the easiest way to do decreasing is to think of a function. Natural log of 1 plus, I'm going to write it as x to the minus 2, just because that's easier to take a derivative. So now we take a derivative of this. So this is 1 over 1 plus x to the minus 2 times the derivative of the inside is a minus 2x to the minus 3. Or I see it's a minus 2 over x cubed over 1 plus 1 over x squared. Now I could do a lot of algebra, I could do a lot of simplification, but if you think about it, we see that this is going to be less than 0 for x greater than 0. Well, whenever x is greater than 0, you look at the denominator. This part right here, that's always positive. This numerator, when x is greater than 0, that numerator is going to be negative, so negative over positive gives us a negative result. And so at this stage, I have what I'm looking for by the alternating series test. The series will converge. Now you may ask, well, what does the series converge to? No clue. We can't tell you what the actual sum of the series is. All I know is that it has a sum. I could approximate it by adding the first however many terms you want to add together, but that wouldn't be the exact value of this series.